And welcome back. We are thinking about the question of the universe, if it started at a Big Bang, must have been very hot and dense in the past. So, what would that look like now? If we look back on it now, what would we see? Well, we can rewind the clock to a point where, I mean, as far back as you want to go, it can get as hot as and dense as you want it to. But there comes a point where you can't see any further back. What is that point? That point is, well, think about sort of looking towards the sun, right? It gets denser and denser as you look towards the sun, as your line of sight goes toward the sun. You can't see the center of the sun. Why not? Because it's layers on top of that that are so hot and dense that light is blocked. Basically, once atoms become ionized, photons, they can absorb photons very easily. And so there should come a point, if you look far enough away, where the universe itself is so hot and dense that it resembles the surface of the sun in that you can't look any further. So if you're playing this forward in time, the universe is so hot and dense that it's opaque. The mean free path of a particular photon is very short, right? It just runs into something. Charged particles absorb any photon. We know that atoms can absorb photons at specific wavelengths, but ionized particles, particles that have charge, like a proton, a bare proton, and a bare electron, can absorb any photon of any energy, of any wavelength. And so at the early universe, it's hot enough that there are no electrons and protons bound together because the photons that are traveling through the universe are high enough energy to break them apart. And so there are these charged particles around, and any photon will be absorbed very quickly. As the universe cools, eventually hydrogen atoms form. Eventually, the universe is cool enough that hydrogen atoms can exist in neutral form. And at that point, the universe almost instantaneously becomes transparent. And then those photons that were emitted at the instant when the universe became basically neutral, the universe becomes transparent. Those photons should still be traveling through the universe today, and we should be able to see them if we can look far enough away. That's the cool thing about this. The Big Bang Theory predicts that the universe should be awash in these photons. Well, what do they look like now? Well, it was very hot at the time. These were fairly high energy photons with fairly low wavelengths. If you remember way back to our unit on light, high energy photons corresponds to low wavelengths. But if you remember how the universe works, as the universe expands, the wavelength of those photons must expand with it. And so since these photons have been traveling now for the entire history of the universe, even though they started out fairly short wavelength, they should have been stretched to very long wavelengths now. And so these should not be visible photons anymore. These should not be X-ray photons. They should not even really be infrared photons. We're talking about the boundary layer between radio and infrared. So let's go to the next slide where we actually see this. The Big Bang model itself predicts a primordial background radiation with a current temperature. And again, this temperature was way hotter when the universe, when these photons were emitted, but all of them have been shifted towards longer wavelengths. And as you know, thermal distributions of photons, we have a nice black body distribution, if you remember that from way back at the beginning of the semester. If you expand and increase the wavelengths of all of those photons, it mimics another beautiful thermal spectrum that just has a much lower temperature. And we the models predict at the time that, okay, we should be able to see this thing. And it should today have a temperature of about 3 degrees Kelvin. It's not even 3 degrees. It's 3 Kelvin. 3 kelvins above absolute zero. And this thing was called the cosmic microwave background radiation. I really enjoy saying that. I'm gonna say it again. The cosmic microwave background radiation, or just CMBR. Why do we call it this? Well, it's a mouthful, but it's fun to say, and it's meaningful, right? Cosmic means universal, of the universe. That makes sense. Background radiation makes sense. This should be a ubiquitous radiation field that's traveling through space. We should be able to see it in any direction that we look. Microwave, why microwave? Well, whoops, pressed the wrong button. Microwave is, we haven't really talked about this, but of course, if you're going from short wavelengths to long wavelengths in electromagnetic spectrum, you have gamma rays, X-rays, ultraviolet, visible, infrared, and then radio. Sometimes people will say, well, there's kind of the transition region between infrared and radio, and call that the microwave region of the spectrum. And so this 3 degree Kelvin black body curve should peak in the microwave region of the spectrum. So we expect it to be in these microwave wavelengths, sort of microns, many microns. And so, right, that's why we call it the cosmic microwave background radiation. Great. This is a nice chart that shows the temperature of the universe as a function of time, seconds since the Big Bang. This is a log scale. It looks like a nice straight line, and it is, but it's not a linear scale. It's a log scale on the y-axis and a log scale on the x-axis. And log scales allow us to do some pretty crazy things, like plotting a huge number of orders of magnitude, right? Look at the orders of magnitude here. From 1, this is in kelvins, 1 Kelvin to 10 to the 31 Kelvin. And an equal number of seconds since the Big Bang almost. In fact, more than that. We've got 10 to the negative 45, 10 to the 15. That's 60 orders of magnitude here on the x-axis. This is pretty crazy. So let's just think about this. 10 to the 0 is 1 second after the Big Bang. That's this line right here. Most of this chart is pre 1 second after the Big Bang, right? And this is kind of crazy because the Big Bang model predicts that the further back in time you go, the hotter it gets. And there's no real end to that. We don't really, well, we'll talk about this in a bit. Right, physics breaks down at these temperatures. Anyway, that's not really the point of this plot. The point of this plot is to show that the further back in time you go, the hotter it gets, and there's no real stop to it. It just keeps going and going. And as you go forward in time, the universe cools off and cools off and cools off. And here we are, roughly 10 to the 17 seconds after the Big Bang, and the universe has cooled to a temperature of about 3 Kelvin. But extrapolating backwards, it gets as hot and dense as you want it to get, to ridiculous temperatures. Where's the center of the sun, right? The center of the sun is 10 million Kelvin, 14, 15 million Kelvin, which is really hot, but that is, right, 10 to the 7, right? The center of the sun is right here. The center of the sun is here. The surface of the sun is more like 5,000 Kelvin, is like right here, right? That is the range of temperatures in the sun. All of these are much hotter than the center of the sun, going again to as hot as you want to go. Crazy stuff. Okay, that's sort of beside the point. We're going to previewing of what's coming next. But the race was on now, right? If you could find this ubiquitous cosmic background radiation coming at us from all directions, then you have the smoking gun that the universe was hot and dense in the past, and therefore the steady state model is wrong, and the Big Bang model it's right. So this was realized in the 1960s. There was a group at Princeton led by Wilkinson who had made these predictions, and they built an antenna. They built a radio telescope on the roof of the science building, and we're just starting to take observations. Now, the story is a nice one, but it doesn't end there. It turns out that these two guys, Arno Penzias and Robert Wilson, were engineers at Bell Labs, and they were fiddling with this antenna. So they had launched some satellites. This is 1965, and they were communicating with these satellites via radio waves. and they had built this horn antenna. This is like a telescope, except it's only one piece of a telescope. And so light comes in, radio waves, which is light waves, comes in, hits this antenna, and is reflected into a detector that's sort of in this building here. Anyway, they were having problems with it because there was noise, right? They were getting this background noise, and they couldn't figure out what was going on. They tried all kinds of things. They cleaned it down, they scrubbed it. There was a nest of pigeons living in here, and so they took the pigeons away and were humane, and I guess drove them down the road 30 miles and dropped them off there. But of course, they were homing pigeons, and so they came back and re-nested, and I guess more drastic measures were taken then. But the point is, none of that mattered. They could not get rid of this sort of hiss that they were still experiencing from this horn antenna. Of course, Wilkinson realizes what's going on, and what they're seeing, this is actually in New Jersey. This is just down the road from Princeton. Comes down and looks at their data, and it's exactly what he had predicted they would see, and exactly the right wavelength to have the predictions of the Big Bang model confirmed. The interesting thing is Penzias and Wilson win the Nobel Prize for physics a couple of years later for discovering the cosmic microwave background radiation, and Wilkinson, who predicted the whole thing, never got it. He got some other things though later on, as we'll see. So it's there. These guys detected a hiss in 1965. This is such an important thing that an entire satellite was launched in 1990 called the COBE satellite, the Cosmic Background Explorer, whose job was to do nothing but map out this radiation and look at it and study it and measure its properties. And this is, so they measured the intensity of the background radiation as a function of wavelength, and this is what they got. So I mentioned it was microns. It's actually thousands of microns, so hundreds of thousands of microns, or millimeters in this case. This is a spectrum, right? This is the intensity, how bright it is as a function of wavelength. And this is now, again, we're talking usually in nanometers when we're talking about visible light. This is now microwave light, far infrared near radio waves. And you can see each of these points is a measurement that COBE took of the intensity at that particular wavelength. And it's stunning, right? I don't know if you remember our models of thermal radiation, but it has this characteristic shape, and it peaks at a certain wavelength. And this particular peak implies a temperature of 2.7 Kelvin, which is, again, very close to what was predicted by the models. And this is still to this day, remember, we're talking about black body radiation, which is what thermal objects emit. We haven't really talked about what black body radiation is. And maybe we talked about why it was called black body radiation. Let me go back and remind you, if I did, and if I didn't tell you for the first time. A black body radiator is a perfect radiator of light, thermal radiator of light. It is a theoretical object that absorbs all photons that are hitting it, and the only photons you get from it are because of its thermal radiation characteristics. And so we have designed black bodies in the lab that are fairly good. Stars are okay black bodies. Meteors, not meteors, but planets and asteroids and things are better black body radiators. But this is a perfect black body spectrum. The uncertainties on these error points, the error bars on these data points, are smaller than the circles themselves. This is the most perfect black body radiation spectrum that has ever been measured. And a Nobel Prize was won for this measurement as well, which is pretty cool. Okay, great. So let's where are we at? The Big Bang model so far is predicted and supported by two major pieces of evidence. And what are those pieces of evidence? Let me remind you. Breaking out the whiteboard for the first time. There we are. So what two pieces of evidence do we have so far that support the Big Bang model? The first one is the Hubble law. Simply having a universe that's expanding, which the Hubble law implies a hot, dense start to the universe and supports and points to a Big Bang model. This was not, although it's extraordinarily compelling evidence, enough to convince a lot of astronomers that the Big Bang was actually a thing. The second one, the cosmic microwave background radiation, was the smoking gun that everybody was looking for, and that pretty much nailed the coffin in any sort of steady state model that you wanted to have. When this was discovered in the 60s, that pretty much ended all the debate. There were no serious astronomers left that were arguing that the Big Bang did not happen. But there's one more compelling piece of evidence that comes from the models that matches today's predictions and observations that I want to talk about. Basically, there's the three pillars of the Big Bang. We've talked about two of them so far. The third pillar we will come to in our our next lecture video. So stay tuned for that.